Hello everyone, welcome back. This is lecture 23 of the lecture series Signals and Systems. So in this video, we will be learning about sampling. I'll be giving an introduction and then we'll see the representation of continuous time signals by its samples. And then we'll see about the sampling theorem and we'll also see the reconstruction of the signals from its samples using interpolation. And also we'll see effect of undersampling, which is also called as aliasing. And then we'll all finally see the discrete time processing of continuous time signals. So let's get started. So until now we have seen continuous time systems, signals and systems, and discrete time signals and systems and their properties, Fourier transform, Fourier series, everything separately, right? So this topic sampling will actually merge them. So we know that in the real world, everything is continuous time. Then what was the necessity to learn about discrete time, right? So what we do is, we sample this. So what is sampling? So we take values of continuous time signal at equal time instance to get discrete time. Okay, for example, if I have a continuous time like this, where this is the amplitude axis and this is the time axis, I will take equal samples of t, let's say. So it is like t, 2t, 3t, 4t, 5t and so on. So I will consider the value only at these points. So now what I will have? Now I will not have the continuous time signal, I will only have the discrete points, the value at these instance. So 0 to t, 2t, 3t, 4t and so on. So I'll have something like this. And so on. So why is this necessary and why is this helpful? So that is what you'll be seeing. So why is it necessary? It's because if we see all our computers nowadays, which does the computation, is done in digital, right? Digital is nothing but discrete time, discrete in time and discrete in amplitude. And over the years, this has grown drastically. Saving time, effort and power in terms of applications. So, doing computation or processing of signals in discrete time is beneficial. So this is the necessity of why we go. And also later on in the chapter we'll be seeing at certain conditions, or we can say with certain conditions, a continuous time signal can be recovered without any loss of information. So this is also a key, without any loss of information, at least theoretically, from a discrete time signal, or we can say its samples. samples of the continuous time signal. And that is why usually what we do is, the real world is continuous time signal, right? We do the sampling, convert it into discrete time, then we do the processing. So this processing is done in a block, right? Computer or whatever device we use. And your output is also some other discrete time. And then again, you can convert back, reconstruct it back to continuous time. Okay. So this is what is currently happening in all of the electronic devices we are using. And that is why learning this topic is very important. So as a first step, we'll first see the representation of continuous time signal by its sample. Of continuous time signals by its samples. So in this, we'll first see how do we do the sampling, how do we represent the samples, right? So for that, we have something called as impulse train sampling. So we know the impulse train. So if we call it as P of t, then we can write summation k equal to minus infinity to infinity delta of t minus kt, right? And in waveform, how will this look like? So you will have impulses with the spacing of t. So 0t, 2t, and on the negative side also you will have this, and so on. And the weights of these impulses are 1 currently, right? So now, using the sampling property of the impulse, right? So if you have a impulse delta of delta of t minus t naught, and if you multiply any signal x of t with it, we know that it will be equal to x of t naught. It will retain only the value at t naught, and the delta of t minus t naught will remain. So similarly, if we have a signal x of t, and we multiply it with, so this is multiply with p of t. One, 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 one. So 0t, 2t, and so on. So this is p of t. So what do we expect to get? So we'll expect to get the values at those instants, right? So only those will be retained. All others will become 0. So at 0 you will have this value. At t you will have this value. At 2t you will have this value. And similarly on the negative side you will have this value. You will have something like this, and it will continue. And you will also have impulses at these positions. So now you can see it is like similar to getting the samples, right? This is what we wanted. We wanted to sample x of t at instance of t, time period t. And that is what we have got. So what will be these values? This will be x of 0. This will be x of t. This will be x of 2t. This will be x of minus t. X of minus 2t, and so on. So if you multiply x of t with p of t is my impulse train, then what will I get? It's like multiplying x of t with summation k equal to minus infinity to infinity delta of t minus kt. And if you take x of t inside, x of t delta of t minus kt, and now you can replace this with x of kt, because only the value at that instant is going to remain. So this is in time domain. And when we look at the frequency domain, there is actually something interesting happening. So let's take a look at that. So we know that multiplication in time domain will lead to convolution in the frequency domain. Let's say I take the Fourier transform. So I'll get x of j omega convolved with p of j omega. So first we need to find what is p of j omega. So from the earlier lectures, if you remember, my p of j omega will be nothing but 2 pi by t summation k equal to minus infinity to infinity delta of omega minus k omega s. And what is this omega s? This omega s is nothing but 2 pi by t. So the Fourier transform of impulse train is also an impulse train, right? But only with a scaling factor of 2 pi by t. So how will this look like? So this will look like 0 omega s, and omega s you can also call it as the sampling frequency, and its units is in radians per second. Sorry, it's in radians per second, and if you divide it by 2 pi, you call something as fs, that is in hertz. Okay, so omega s is the sampling frequency. Okay, so you have omega s, 2 omega s on this side as well, and so on. And you have an impulse train again here. Only that now this is 2 pi by t. Each of them is 2 pi by t. So now what is the resulting x of t into p of t? If I call it as y of t, x of t into p of t, then y of j omega will be x of j omega convolved with p of j omega. We already got what is p of j omega, and it is here. So x of j omega convolved with 2 pi by t summation k equal to minus infinity to infinity delta of omega minus k omega s. So now if we take this inside, since 2 pi by t is constant and x of j omega doesn't depend on k, so we can take this inside. So I'll get x of j omega convolved with delta of omega minus k omega s. So this is just an impulse. So convolution of anything with an impulse will just give a shifted version of the signal, right? So it will be 2 pi by t summation k equal to minus infinity to infinity x of j into omega minus k omega s. And if you recall, we actually forgot a factor of 1 by 2 pi. So this will be 1 by 2 pi into convolution of this. So here also we'll have that 1 by 2 pi factor. Similarly, carrying it through, we'll only have 1 by t here. So this is our y of j omega. And what is y of j omega? It is nothing but the sampled Fourier transform of the sampled x of t. So this one. So I can call it, choose to call it xp of j omega. If I call xp of t as the sampled version of x of t, then I can call this as xp of j omega. So here also I'll call it as xp of t. Okay, so this is my Fourier transform of sampled x of t, which is nothing but equivalent to xp of t. So let us try to interpret this. So let's say my x of j omega is something like this. It is band limited signal, band limited to omega m. And what will be my xp of j omega? So if you see, it is like shifted versions of x of j omega by omega s, and scaled by a factor of 1 by t, and they are all summed over. So if I need to write omega s, 2 omega s, minus omega s, minus 2 omega s and so on. And if I say my omega m is less than omega s by 2, so it is somewhere here, less than here. So my first one for k equal to 0, I'll get the same thing scaled by a factor of 1 by t. And then my next I will get at omega s, 1 omega s, and next one is at 2 omega s. So I'll get the replicas of this. So if this is 1, this will be 1 by t. So this will be 1 by t, and it will be same on the negative side also. So here if it is minus omega s and this is minus omega s by 2. So I'll get something like this. This is minus 3 omega s by 2. I'll get something like this. These are all scaled versions and shifted by a factor of omega s. So now let's say I want to go back from this to this. What do I do? Can you see a good way to go back from here to here? This is all still in continuous time. Since we are using omega as a continuous variable, right? We haven't gone into discrete time. So what can be done? Yes, it is very easy. Just pass this xp of t through a low pass filter with cutoff frequency at omega s by 2 and minus omega s by 2. And with gain as t, because you need to bring 1 by t, 1 from 1 by t. You need to bring 1 from 1 by t. So you have to multiply it with t. So low pass filter. So you need to pass xp of t through this LPF to get back x of t, right? But there is a catch here. Can this be done for all signals? So we have assumed one thing, right? Which is nothing but my omega m, my band limited signal, the bandwidth of my signal, input signal, is less than my half of my sampling frequency. In other words, my sampling frequency should be greater than 2 times the bandwidth of my signal, right? Only then it is possible. Let's take the case when omega m is greater than omega s by 2. Then what happens? So you again have 0. I'll only show omega s. Sorry, I will not be showing the 2 omega s. If you want, we can go. So now my omega s by 2 is here. So now my signal bandwidth is actually beyond this. It is going to extend. And what happens to my replica at omega s? So that is also going to come here, right? And my at 2 omega s, that will also be seeping through this. We don't want this to happen. So now what is happening? These are overlapped. So what will my final signal look like? So it will look like, so here also there's something coming from there. To look like this. It will be constant, right? And it will go up, come down, again be constant, go up, come down. So my signal will look like this. So this is at 0 omega s, minus omega s, and so on. So now if I put a low pass filter at omega s by 2, with a gain of t. So this is anyway 1 by t. So what will I get? My recovered signal will be something like this. This will be 1. So this is nowhere related to my original signal I started with. So that is the condition. So this condition is very strict and we must follow this to, if we have to recover back the continuous time signal which we started with. So this signal is not recovered properly. So now we have the sampling theorem. So it says let x of t be a band limited signal. Band limited is nothing but it is limited to certain frequency. So there are some signals which do not end at omega m, right? They can go up to infinity. So they are not band limited. But these kind of signal, if you see, they are going to be band limited to omega n. So if x of t is one such signal where it is band limited with x of j omega equal to 0 for mod omega greater than omega m. So this omega m is the bandwidth of the signal. Then x of t is uniquely determined by its samples x of nt for n equal to 0, plus minus 1, plus minus 2 and so on is my sampling frequency omega s is greater than 2 omega n, and omega s is nothing but 2 pi by t, where t is my sampling period. And given these samples, I can reconstruct x of t by passing the sampled impulse train, right? The sampled impulse train xp of t through a low pass filter with cutoff frequency ideally it can be omega s by 2, but it can also be somewhere here, right? So if you see, it can also start from here, so it is not a problem. So it should be somewhere between omega s by 2 and this place is omega m. So it should be somewhere between that. Or if it is coming until here, then it can also be between omega s by 2 to this point. This point will be minus omega s plus omega m, right? So that way. So in generic case, I'm just writing omega s by 2. And this frequency of 2 omega m, right? So omega s equal to 2 omega m is called as the Nyquist rate in terms of sampling, and omega m itself is called as the Nyquist frequency. So the Nyquist frequency is half of the Nyquist rate. So in this case, for sampling we have used impulses, but in the real world or in the real scenario, if you see, impulses are not easy to generate. So then what we do? So we have something called as the zero order hold. So where we can sample and hold the value. So how do you do that? If you have a cap and if you have an input signal coming here, x of t, you sample this and you hold it on the capacitor. Once you release it, the voltage is going to be held here, right? So if I draw it in a waveform, so if I have this as x of t, and these are my sampling instances. So I'm first sampling here and I'm going to hold this value until the next sampling edge comes. And then again I sample this value and I'm going to hold it here. And again here I'm going to sample this value, hold it here until this comes, and here I'm going to sample and hold, and here I'm going to sample and hold, and again here I'm going to sample and hold. So this is what my output will look like. So here what is my sampling waveform? It is gonna be, I'll call it as h0 of t. So this is 1 and this is from 0 to t. So I'm going to have a shifted versions of this and then multiply it with my original signal, right? So this is like my impulse response for this kind of sampling. So in the place of delta of t, right, if we have p of t, we had summation k equal to minus infinity to infinity delta of t minus kt. So in place of delta, we are going to have this h0. So it will be h0 of t minus kt. So my final xp of t will be summation k equal to minus infinity to infinity x of kt h0 of t minus kt. So in essence, you are first doing the impulse sampling and then you're passing it through this kind of filter to get this kind of waveform, the one shown in red. So I can also name this as x0 of t. So I have x of t. I first multiply it with my p of t, which is my impulse train. I will get xp of t. Now I pass this xp of t through this h0 of t. And then I'll get this x0 of t, which is shown in red in this figure. So this is how you can mathematically represent this. And how will you recover back this x of t again from x0 of t? In essence, you are again going to pass this through another low pass filter with, let's say, transfer function h prime of j omega, and you need to get x of t back. So your x prime of j omega should invert whatever was done here, the multiplication with p of t, and then passing it through this system with impulse response h0 of t. So let us see what is this h0 of j omega. So if you have this one, minus t by 2 to t by 2 with value 1. So this is gonna give me a Fourier transform of 2 sine omega t by 2 divided by omega. But what is my h0 of t? It is shifted by t by 2 to the right, right? So h0 of t is 0 to t. So the Fourier transform of this will be e power minus j omega t by 2 into 2 sine of omega t by 2 by omega. And we already saw to invert this p of t, it was just a simple low pass filter with value 1 and cutoff frequency at omega s by 2. And to invert this, what we need to have, the h prime of j omega should be 1 by this, right? So it will be e power j omega t by 2 by 2 sine of omega t by 2 by omega into the low pass filter which we already have. So this h of j omega is something like this. So this is what we want. So in the impulse train sampling case, we only had this, but in this case, the final low pass filter should have something like this. And how will this look like? So this h prime of j omega will look something like this. So if I take only the magnitude, right, it will go from minus omega s by 2 to omega s by 2. And then it is having kind of the sink will be like this, right? But this is 1 by the sink function. So it will be something like this. And for phase, you have a linear phase. So which is starting from at minus omega s by 2, it will start from minus pi by 2. And at omega s by 2, it will reach pi by 2. So again, what this is trying to say is, if you use a different kind of sampling techniques, let's say you needn't be this, it can be a linear sampling, right? From here to here you can join, here to here you can join, something like that. Then your whatever the low pass filter you are using to get back your original signal will differ accordingly. So that is what this is trying to say. So next we'll only study more elaboration of this concept, which is nothing but the reconstruction of a continuous time signal from its samples. And we call this method as interpolation. So this was also a kind of interpolation only. So if you just add these samples, so what this is saying is, you just do something, create something like this from this, right? You create something like this, and then you pass it through some low pass filtering. So what a low pass filtering does is, it smooths out the waveform, smoothens a waveform. So then you will not get these discrete points. So you'll get something smooth like this, right? So this is what you will get. So that is what we are trying to see here also. So in the previous case, it was called as zero order hold. And we'll see something now like linear interpolation. So in this, what we do is, we have the points. So let's say these are the points. Now what we do is, we just connect these points together by a line. From 0, let's say this thing, from here to here, we use a linear line to connect each of these points. So this way it will keep on going. And then what we do, you pass it through an appropriate low pass filter. So now this low pass filter, if you want to get the signal which you sampled exactly, it should have something similar to this thing, right? It will have its own transfer function which we have to use to get back the original signal. But in most cases, if accuracy is not necessary, you can just pass it through some generic low pass filter. Of course, it should be somewhat close to what is expected, and then you will get some smooth curves like this, right? So this is called as a linear interpolation. So going back to our sampling theorem, we said we can get back our original signal if our sampling frequency is greater than 2 times the input bandwidth, right? The signal bandwidth. And we said for the impulse train sampling, we'll use a simple low pass filter with cutoff frequency at minus omega s by 2 to omega s by 2, and with gain of t, right? So now we'll look at that. So we have our x of t, and we sampled it to get xp of t, which is like an impulse train sampling. Now we need to pass this through a low pass filter having this kind of frequency response. And then we said we'll get back x of t. For now, let's call it xr of t, and we'll see how xr of t is equal to x of t. So my xr of t is nothing but xp of t convolved with this transfer function. So impulse response h of t. And if I have to write this out, this will be summation n equal to minus infinity to infinity x of nt h of t minus nt. You can think why this is so, because my xp of t is nothing but sum of impulses with scaled version of x of nt, and impulses convolved with h of t, any signal will give the shifted version of the signal itself. So that is how we are getting this. And my h of t I need to get. So if this is my frequency response, if I take a inverse Fourier transform, what will be my h of t? It is going to be a sinc waveform. So to say it exactly, it will be sinc sine of omega ct by pi t, but we also have a gain of t. So this will be my h of t. To represent it in the form of sinc, I just multiply and divide by omega c. So omega ct sine of omega ct by pi omega ct. So if I try to substitute it back here, I'll get xr of t is summation n equal to minus infinity to infinity x of nt into omega ct by pi into sine of omega c into t minus nt by omega c, this is small t, into t minus nt. So this is just a shifted version of sinc. So my sinc, how will it look like? It will look something like this. It's a dying down sine waveform. And I will have nulls at 0, ts, 2ts, and here ts is nothing but t. Omega c is 2 pi by t, so it will occur at t. So 3t, and on the negative side it will be minus t minus 2t and so on. So now if I take for each of this, so it will, for x of 0, it will be x of 0 into this. The scale, it will be scaled by x of 0, and then it will be scaled by x of t and so on. And if I take them everything and add them up, let's say at x of 0 it is something like this. This is x of 0, and at x of t, if I see, let's say it is something smaller. So this is x of t, and then if I take some other color, x of minus t, t minus t, let's say it is something here. So I'll get, similarly constructing it everywhere else, I'll get something like this. And once I add them up, I'll get the signal back. So the signal will something look like this thing. And if you see at the sampling points where we have sampled, only that particular value is coming and everything else is going to be 0, right? At x of 0, at 0, only x of 0 is coming and everything is having at null at that place because of the sinc function. And if you see, also see at x of t, at time instant t, only x of t is present and all others are going to go to 0. So using this interpolation, we can say that your xr of nt is always going to be equal to x of nt without any doubt. And all other places, what it is doing a sinc interpolation. So you only have values at this, and using sinc, you're going to reconstruct, and then hence it is giving something of a smooth out nature, right? And if your original signal was band limited, this is gonna be exactly equal. The xr of t is exactly gonna be equal to x of t if sampling theorem conditions hold. right? So this is just to show you that in frequency domain, it was easy to see. You just put a low pass filter, you're only getting that whatever is there between minus omega s by 2 to omega s by 2, you're having a gain of t. And you're getting back x of j omega. But in the time domain, what is happening? This is what is happening. It is kind of a sinc interpolation which is happening. So this is very interesting to see. So now let us again revisit the zero order hold. So here the interpolating function is sinc, right? So for impulse, okay, here I will say sampling signal used. The signal we use to sample it, and then this is whatever the interpolating signal. So for impulse train, we had sinc, and for zero order hold, we had the waveform like this, right? H naught of t. And for linear interpolation, I'll have something like this. Minus t to t with 1. So at 1 I'll get that point, and at t I'll get, at t by 2 I'll get the average of this and the next point. At t this will not come, only the next point will be available. Similarly on the negative side. So this will be my h of t. I'll call it h1 of t. So if we see the low pass filter of these, so this is gonna be minus omega s by 2 to omega s by 2, and with the value of t. And for this one, what is the thing? It is gonna be a sinc, right? So it will be something like this. If you only take the magnitude, it will be like this. And for the linear one, it is, you can see it's like a convolution of this with itself. So it will be of this itself, but of the second order. So it will die down faster. Right? If I have to put this on the same thing, right? Just to compare, I have this for zero order hold. I will have something like omegas. This is omegas by 2, right? So I will have something like this. Sinc. So here its value is t only. I'll have a sinc. And for linear, I'm going to have a square of this. So at higher frequencies, it is actually be closer. When you come lower and lower, it is gonna smoothen out. I'll have something like this for the linear interpolation case. So you can see this much is the error we are making if we leave the signal as it is. So after you have applied the zero order hold and linear, you have to pass it through another filter such that the multiplication of this one, this zero order hold with the new filter will give me back this ideal filter to, if you have to reconstruct the signal ideally, right? Otherwise, if you only pass it through this one, you will just get these kind of signals. And in the linear case, you will get this kind of signals, right? So that is what you need to understand. So next we'll quickly see the effect of undersampling. It is also called as aliasing. So everything is fine. If we sample omega as greater than 2 omega, it's good. But what happens when omega is less than 2 omega? Let us try to understand that. So for that, we'll take a simple example, cos of omega naught t. So let's say my x of t is cos of omega naught t, and at first let's say my omega s is some 2 omega naught or 3 omega naught. So then what will my xp of j omega look like? So my x of j omega itself is, I will have an impulse with value half, right, at omega naught and minus omega naught. And xp what it will have, this will just repeat at intervals of omega s. So omega s minus omega s. So now this will come at, so my omega naught is omega s by 3. So this is like 3 omega naught. So my omega naught will be somewhere here, minus omega naught. My 1.5 omega naught will be somewhere here. This is omega s by 2. And if I put a filter here, so this is my this thing. And whatever I have at omega s will come here. So this will be at my 2 omega naught. This is at 4 omega naught. Similarly here also, minus 2 omega naught and minus 4 omega naught. This is half and half. So if I put a low pass filter here, I can reconstruct it without any problem. So can be reconstructed. Ideally. So now if I take a case where omega s is some omega naught by 2. So omega s is equal to omega naught by 2. Or if it just needs to be less than 2 omega naught, right? If I take it also 3 omega naught by 2, then what happens? So let us see that. So I have 0, I have omega naught here, and minus omega naught here. And this is nothing but 1.5 omega naught. So where it will come? It will come somewhere here, right? Here omega s, minus omega s. This is 1.5 omega naught, minus 1.5 omega naught. So now where will this replica at omega s sit at? So it will sit at omega s minus omega naught, which is 0.5 omega naught. So it will come here. Omega naught, 0.5 omega naught. So I will represent it in red. On the other side, where it will come at 2.5 omega naught. Similarly, for minus omega s by 2, it will come at 0.5 omega naught, minus 0.5 omega naught, and 2.5 omega naught. Now, what will be the filter cutoff frequency? It will be omega s by 2, which is nothing but 0.75 omega naught. So it will be somewhere here. So I am cutting off somewhere here. So what will be my signal now? It will be minus 0.5 omega naught and 0.5 omega naught, which is nothing but cos of 0.5 omega naught t. But this is not what I started with. I needed cos omega naught t. But what happens? I am getting cos 0.5 omega naught t. So as you can see, as expected, we are not reconstructing the original signal we started with. But what other interesting thing is also happening? You can see that the frequency has reduced. And the other interesting thing, if you have a phase plus phi, what happens? Here you will have e power j phi and e power minus j phi, right? In the original signal. But this one will be here, this one will be here. But when it is coming here, this point will be e power minus j phi, right? So this one would contain e power minus j phi, and this would have contained e power j phi plus j phi. So you will also have a phase reversal. You will get minus phi here. You started with a plus phi, but you are getting minus phi here. So these both things can happen when you have a aliasing. So to see a real life example, if you have a rotating fan, so rotating fan clockwise, it's rotating clockwise. Now you take a video. So it is, let's say it is rotating at certain frequency omega m. Now if you take a video, so in video you have frames per second. So if you restrict it such that this is like, it will capture at every instance of this frame. If you have 30 frames per second it will take 30 frames, which means there is one picture taken every 1/30 seconds. So this, if you restrict such that the angular frequency of your sampling is omega s, which is less than 2 omega m, then you will observe that the fan is actually slower than it is running, slower, and also it is rotating clockwise. But here in the video it will show that it is as if rotating anti-clockwise. Right? Because let's say in frame 1 it will be here, let's say the 3 sticks are here. In frame 2 it will be, it would have completed almost one rotation, but it is like, it is captured here just before a time instant, so that it is as if appearing that it is moving in anti-clockwise direction. And if you say omega is actually equal to 2 omega m, then what happens? The fan will appear to be stationary. So then also you cannot recover. So that is why it is strictly required that omega s needs to be greater than 2 omega m. We are not even saying greater than or equal to. It is strictly greater than 2 omega m. So this is all about aliasing. Next, let us move on to discrete time processing of continuous time signals. Discrete time processing of continuous time signals. So here, as I already explained in the starting, what we do is we have a continuous time, and the need for this is because, again to reiterate, discrete time processing is easier than continuous time processing. It is more vast, and you have all the research available. You have more easy methods to do it conveniently. So you first have the continuous time signal, which you convert to discrete time signal. So you have a continuous time to discrete time conversion. So then you will have your discrete time signal, which you take it through a discrete time system. And then you get your output in discrete time. Then you take this and you convert it back to continuous time. So discrete to continuous time conversion to get your output. So in effect, this is what you want to achieve. And your xd of n you can directly get from your xc by sampling it at time instance of t. Similarly, your yd will look something like yc of nt. So again you have to interpolate this to get your yc of t back. So got by interpolation from yc of nt. And all along this process, your sampling theorem condition should hold to actually perform the required h of j omega. So the continuous time of computation, whatever processing, whatever you have to do to get it properly, your sampling theorem should hold. So mathematically, if we derive, we will get a relation between h of j omega and this, let's say, this is hd of e per j omega. So mathematically we will see how to get this relation between h of j omega and ht of e power j omega in the next class. So until then, take care. Bye bye.